Welcome to How to Succeed in ECE Without Really Trying. I'm Dr. Linda DeBrenner, and in this video, I'll be talking about second-order transients. Let's consider a circuit with both the capacitor and inductor. So here we have a simple circuit with a capacitor and inductor in series, along with the load resistor R. We define the input to be the voltage applied to the beginning, to the input, and then the output voltage is VO. When we do this analysis, we're going to end up with a transfer function that has S squared terms, one or more, is like either in the denominator or in the numerator. And this causes the circuit to resonate at a particular frequency. We'll also see the damping effects we saw both for the RC and RL circuits. So here's our circuit. We're going to go ahead and again write an equation going around the loop. VI of t is equal to Vc of t plus Ldi dt plus Ri of t. Remember, of course, for a capacitor that I is equal to C dV dt. Now we can take the derivative of both sides of the equation and use the dot notation for convenience. So we end up with dV of t dt, which will denote V dot of t, is equal to 1 over C I of t plus L double dot I of t, I double dot of t, which is the second derivative of I of t, plus R times I dot of t, again the first derivative of I of t. So we can write that more simply as, by dropping the t's, Vn dot is equal to 1 over C I plus Li double dot plus Ri dot. So this is a second order differential equation that describes the full characteristics of the circuit. Notice that V out does not directly appear in our circuit solution, but we can define it as V out of t is equal to Ri of t based on Ohm's law. We can solve this differential equation, and it proceeds in the same way that we did when we solved the RC circuit and the RL circuits. Of course, this time we're going to have two time constants, and these will be the solutions of the characteristic equation, which was Ls squared plus Rs plus 1 over C. These solutions will have characteristics that depend on the circuit element values, and specifically we know that when CR squared minus 4LC is greater than or equal to 0, then the two roots will be real. Okay, and the solutions will decay as before, dominated by the smallest time constant. So in general, we have damping, which is what engineers usually use the term damping instead of the term time constant. But damping can have three cases. Critical damping occurs when CR squared minus 4LC is equal to 0. Overdamping occurs when CR squared minus 4LC is strictly positive. And underdamping occurs when CR quantity squared minus 4LC is negative. In this case, the roots will be complex. So here's a graph showing critical damping when CR quantity squared minus 4LC is equal to 0. You can see that the output follows the input very, very closely. The underdamped case occurs when the value CR quantity squared minus 4LC is negative. In this case, we've plotted the case where it's equal to negative 4 times 10 to the minus 9th. In this case, we see that the output overshoots the value and then gradually oscillates. It oscillates as it gradually approaches the final value and approaches the value it should be. We can zoom in on the oscillation portion and see the frequency of oscillation from the graph. Finally, let's consider the overdamped case where CR quantity squared minus 4LC is a positive value. So here we plotted the value 9.6 times 10 to the minus 8th. You can see that it takes longer to achieve the final value. Using our knowledge that we developed in the section on passive filtering, we can also write these equations as well. Using KVL, we can write that I is equal to Vn over R plus SL plus 1 over SC. Okay, multiplying through by SC over SC gives us I is equal to SC Vn over S squared LC plus SCR plus 1. Realizing that the output voltage V out over R is equal to the current, we can solve for V out over Vn, and we get SCR over S squared LC plus SCR plus 1. If we substitute in omega equals 0 and omega approaches infinity, we can determine that this is a bandpass filter. If we consider the voltage across the inductor as the output, we can write H of S for this new value, this new transfer function, is S squared LC over S squared LC plus SCR plus 1, which is a high-pass filter. Using the voltage across the capacitor as the output, we get the transfer function 1 over SC over R plus SL plus 1 over SC, which simplifies to 1 over S squared LC plus SCR plus 1, and this is a low-pass filter. And finally, if we use the voltage across the inductor-capacitor pair, we end up with a transfer function SL plus 1 over SC over R plus SL plus 1 over SC, which simplifies to S squared LC plus 1 over S squared LC plus SCR plus 1. This combines a high-pass filter and the low-pass filter transfer functions and gives us a band-stop filter. Thanks for watching.